People get hurt every day doing this stupid ass.
Today's Captain's blog is made possible through the support of Daniel D. Jager and dozens of other people just like you on Patreon. If you're interested in supporting this video and other ones like it, check out the links below in the description and see how you can get involved. Thank you.
Hi there guys, welcome to today's equipment autopsy. Today we have a really nifty little altimeter. This is a standard aviation altimeter, and let's see who made it. Oh my god, it's made by Square D. I was not prepared for that. It's a Square D company. It's not the actual Square D company, it's like a division of it. This is so cool. I'm going to take this off and see if I can get a super pretty shot of it. But the first thing I'm going to do is take the maker plate off of it, because I was not expecting Square D. As a guy who uses and is a huge fan of a lot of their products, particularly their circuit breakers, this is made by Square D. I didn't know they made aircraft stuff. I didn't even know they had a division that made aircraft stuff, but let me get a picture of that. That's cool. All right. All right, so we've got our little maker plate off there. We'll check that out in the future, but this is an altimeter. Now, an altimeter is a piece of avionics equipment which is used to tell you how high above the earth you are. And it works on barometric pressure. Now, you can get different types of altimeters, especially today. We have GPS altimeters and stuff like that that work from the satellite constellation. But this is an old school altimeter, and it's last calibrated in 1994. It's probably older than that, I would imagine. And it's made by Kollsman, K-O-L-L-S-M-A-N, which is apparently a division of the Square D company. And it looks relatively simple. Now, before I open this up, I want to show you how it works. So this, they're rock simple. It's got one knob on it, and you adjust the knob to match your barometric pressure here. So if you look on the front, you can see we've got hands like a clock, big hand, little hand. And as I move this knob, the hands move, and so does this over here. So what that is your air pressure at this moment for wherever you are. And that's how you calibrate this so that you know it's reading accurately, which is why if you listen to air traffic control stuff, you'll frequently hear them give the air pressure at the airport so that the guys in the airplane, the pilots, can calibrate their altimeter perfectly so that the altimeter is reading accurately when you land. Because it doesn't matter, like a difference between 11,000 and 11,050 feet doesn't matter a lot, but the difference between the ground plus or minus 50 feet really matters. And a fun thing to do, and I've actually done it with altimeters, probably even this one, is you take an altimeter and you set it accurately on, like, I don't know, Monday, and then you come back a week later and it's different, it drifts, and it'll say that you are, that you've physically moved location in elevation, even though you haven't. And the reason is because air pressure changes. So you can use a barometer for an altimeter, and you can use an altimeter for a barometer. And really, these old school altimeters, all this is a barometer with a different readout. So we're going to open it up and see how that works. Ooh, I get to do a thing you're never supposed to do, ever, ever, ever. And I'm going to do it before I open this up. So on the back, you can see there's a little plug. We're going to pop that little plug out. And inside the plug, you can see that there's a hole and there'll be an orifice somewhere off there. I can't spot it at the moment, but somewhere in there, there's an orifice that goes off. So the one thing you should never, ever, ever do is A, stick anything in there, and B, blow in there. For the love of God, never do that. But if I blow into this, you should see the needle move. Now, I don't know if you saw the needle move or not because I can't see that, but I'll bet you did. I'm just going to have faith in the science and my embouchure and assume the needle moved. And the reason the needle moved is I blew in the hole. If you change the air pressure on this side of the hole, you change the whole thing. All right, I think this is the last one. Get that out. And now, I may have to take that out too. No, you're in there. Tappy, tap, tap. Oh, we got that. All right, it just took a little love and possibly snapping what I imagine to be a little gear trapped down in there off of that. All right, so we're in a very thin seal. And we just got to pop, there we go. Okay, so our glass is off and now we're into the envelope. I'll walk that out. And that may be what held it in. I want you to come out of your box so that I may share you with the world. Well, it's in there. Question I have is, what holds it in there? You may have to keep taking bits apart from the front to find out. I'm going to need a smaller screwdriver than that. Alright, so let's get in here with a special, super tiny little screwdriver. See if this will do it. Got it. All right, now I have a little ray of hope. These pop off like clock hands. There's a third. There's a third. I've never seen a third before. All right. So now we're getting into it. This is neat. That's just a little, looks like phosphor bronze spring maybe. There's our readout. I'm gonna very delicately, very carefully lift that out of there. So that's a mask. And then here's the whole, look at the gears. I was not anticipating this level of clockwork awesomeness in here. The back of that's a big ring gear. Wow, look at the frame. This is cool. This is super cool. I'm impressed. We got a whole gear train, and there's little microscopic gears in here. I don't want to just take this apart top down. I want to have the whole mechanism out so we can see it and explore it and share it. And maybe this piece of metal wedged in over here is what's holding that all in? Maybe? No, because it's not set in a ring or anything. You are, though. See that ring down the bottom there? That might be our retention. Because what I'm hoping is there's some way I can just slide this all right out. But I don't just want to gut it from its mouth one piece at a time. I really want to show mechanisms working. Oh, you're moving. Please be what I think you are. Okay, a little spring. Wait, I see a hole. If that moves, does that move? Does the other side move? Yep, that's what I thought it was. Oh, this is going to be a pain in the ass. Alright, so it is retained in. That's a spring clip, so I got to pull those two together. I think I have a tool for this. This is a bad idea, and people get hurt doing this silly shit. People get hurt every day doing this stupid ass shit. But we're doing it because it's the best way I got to do it. So, first thing I'm doing is putting on safety glasses, because this is where we get little tiny pieces of metal flying around, and guys with my job end up blind. So I'm going to see, will you fit in there? Alright, we're going to try this the easy way first, because I happen to have a micro set of screwdrivers right here. And I'm going to see if I can fit two of these in holes. So we put one in here, and one in here. We're going to see if we can just walk this right on up and out. Oh God, I might get lucky. Oh, come on. Come on, baby. Oh, wow, that never happens. Never happens. This is just a really soft spring. Oh, cool. Okay, so we want to let it not snap down back in there. And we're just going to walk it out. Oh, come on. Come on. I just want to share you with the world. Yes. Look at that. We got it. That right there is the brass ring. That's, okay, so with that out of the way, I think... Fuck. It's going to come out in some manner of pieces. Oh, it's going to come out in a lot of pieces. No? Maybe. Oh, wow, just two. Okay. And then we've just got some gears and... Well, that's brass. You can see the difference in the color there. That's brass. And that's another little snap ring. So that's what holds it in. So on the front... Oh, I'm so glad I got that out. I'm so happy that that just actually was able to do that. Okay, so we've got... Let's break this down. On the front, we've got basically a clock face. And there's some really nifty little tiny gears. Tweezers for scale. Some really tiny little gears in there. And this is literally clockwork stuff. So we got some really cool tiny little gears, and those arrange with the hands, of which there are 3. Have never seen the 3rd hand on an altimeter. That's kind of fascinating to me. So we got our gears on the front face. That's the clock face. And then we have what drives the clock face. Now here, we've got a counterweight. Now, can I don't think I can, but let's try. I don't think this will work. Okay. Oh, it does. Okay. So there's our hand for our altimeter. And you can see it takes a very, very small amount of input back here. So let's look at what we have. This is a set of bellows. So this is 6 little pieces of copper soldered together to make one crinkly side can. Now, if we filled this with water and squeezed it, the water would squirt out, right? Because we've got a hole in it, and our hole is back here. This is our hole. So if we filled this with water and squeezed it, water would shoot out here. But, and here's where it gets cool. If we suck on this, this will shrink, because this will compress together. You can see it'll move just a little bit, but we don't need it to move a lot. And I don't want to reef into it because we'll get to why. So what you do is you put this in a can, this can, okay? And on the outside of the can, you have a hole that connects to this, and the inside of the can is sealed off from the outside of the can. So if you take this up high in the air, where the air is thinner, this is going to change size because you still have more, at that point you have more air pressure in here than you do outside, so this is going to compress. If you go lower, air is going to come in because the pressure is higher out there, so this is going to expand. And all this does is very accurately measure the distance across the top and bottom of this little can. You're just measuring the expansion. So if I squeeze this, if I just touch this just the slightest bit, you see that needle moving behind there? Watch. We'll do it from the side. If I just touch this with just a fingertip, you can see that needle move. Okay? And it really doesn't take a lot. If I squeeze this with, let's say, a pound of force, we move all the way around. So there's this whole complicated linkage, and this is where things get really cool. So what we're doing is the goal, the object of this whole assembly is to measure the position of this point right here on top relative to this point on here. And you can see this is anchored rigidly to the big, I'm going to say that's bronze, maybe copper. It's a little light for just copper. But this is our big immovable object frame, right? So this can expand and contract here. And this part right here moves in a straight line relative to here. So now what we need to do is take this tiny little up and down movement and translate that to a whole hell of a lot of roundy round movement. So the way it does that is we have this little arm, and there's a pivot down there. There's a tiny, tiny little pivot pin. Look at that. And that goes up to this here, which is another pivot, which turns this shaft on this pivot. Now that's a jeweled mechanism there because you can see we've got this little bolt goes in, that's going to have a receiver in there, and it's probably jeweled. It might be, it might not, but frequently you'll see little tiny pieces of synthetic jewelry, like a ruby or a sapphire. You'll see these a lot in wristwatches as a bearing. And when you get into avionics stuff, you're well into the we don't care what it costs, just make it reliable and make it work right. So stuff like that, totally cool. And then that shaft moves across this, and I can't figure out just what the hell that is. Oh, it's this whole big thing. Look at that. This is a big chunk of metal here that's a counterweight. So it's on a spring. There's a lot of mass to it. It's crazy big and heavy for something on such a delicate little thing. So this, and when I move it, it moves the thing. This is probably, you've heard the term in Star Trek, inertial dampening. This is inertial dampening. You use a big heavy thing to keep a tiny thing from jiggling around too much. So this is probably some kind of damping. And then the shaft goes on through to a spring here. Now this is a spiral spring. Way in the back. That's a spiral spring on this shaft. And then this shaft, this is where it gets cool. Here's our shaft, and you can see our spiral spring and our counterweight on the shaft right here. That goes all the way down, and there's a gear here. That's toothed. That whole big thing. And that gear circumscribes an arc of like 45 degrees. It goes all the way from up here. Let me see if I can move it enough so you can see the other side. I got to push it from the side. I got to get behind the thing. See the other side of that gear? Way over there. It's like 45 degrees off. That's a huge arc with little itty bitty teeth. That's crazy. So this here turns this, and you can see we turn at a point really close to the shaft. And that's important because the distance of this lever equates to a force magnification. Or, yeah, think of it like a magnification, because this lever is really tiny. So the distance from here to here, the radius from the center of the shaft out to here, is much shorter than the radius from the center shaft, which is right here, way the hell out to the end of this. So, watch. That moves the shaft through, let's say, 45 degrees, right? And that's a huge motion out on the end. We're moving a distance of like 2 inches, 2.5. But that same motion, when viewed from the back, let me pinch my little thing here. Look at how little we move that thing. See, it just moves a little bit. That's so cool. And you'll notice we're actually moving through this slot. We're not moving the thing yet. If I move the thing, everything else follows suit. But there's this free pass area where nothing happens. Okay, we're not actually measuring the movement here. If this expands, it'll push that up. But if this contracts more, it's not really going to pull it down a whole lot. Now comment in with the reason why they would want to do that. I'm going to leave that as the puzzle for you guys. But there's a reason. It's an important reason. So why would this not be a rigid link? You can see there's a little pin right there. But why is this not a rigid link all the way through? Like I can squeeze this against itself and move all of that. So we go from there on our big arc gear that engages down in here. There's a little tiny pinion gear. Crazy tiny pinion gear. And then that's just on this big bowl gear here. And the big bowl gear turns another little tiny pinion gear way up there, way up in the middle. You can see it at the end of my tweezers, right? If I get my damn tweezers in there, you can see it right up in there, right at the middle, the bottom of this shaft. And that gear is what turns the shaft. And then there's another gear out here. Now this gear works with all the stuff we saw in the front. That's where you get into this gear and all that. And all that's doing is the gear reduction train for the different hands. So that like this hand goes around one time and the next hand moves a little bit and the next hand moves a little bit like that. But yeah. So an altimeter measures barometric pressure. Well, it measures altitude via barometric pressure. And this is our pressure vessel. And that works through a set of linkages and cams and springs and all kinds of really fascinating tiny bits to activate that big needle. So here's a fun question. Now that we know all that, what does this big gear on the outside do? It would want to rotate this whole assembly. What does this big gear do? Can you figure it out? I bet you can. Think it through. Go back to the beginning and think from there. And then tell me, what does this big gear do? That's pretty cool, isn't it? I think it's fascinating. I think it's beautiful. It's all copper and bronze and brass. Now, why would they use those metals in here? Why isn't this just made out of aluminum and steel? Both are pretty cheap. Why use the expensive metals like bronze and brass and copper? Those are the three that I see the most of in here, is because we have, this is brass, and that's nice yellow brass, and this is very obviously copper. And this stuff looks like bronze. The colors are a little bit different. So why the different colors? Why this here? This is definitely made out of phosphor bronze, but there's an easy reason for that. We know this is phosphor bronze because it's a spring. And you don't want to make springs out of copper. You can, but it's going to suck. So why would they choose these metals? It's so beautiful. There's so much going on here. Like, check out the little compression struts. These little pins fit in tiny holes, and there's 3 different holes to choose from so they can adjust it. And the other end fits in here. And these just lock this all together in a way where it can move. Because as this comes up and down, these will move in and out. So this is a spring, and these are of a sort springs. And this little yoke on top is adjustable off that screw to expand the little yoke clamp here. Like, there's a hell of a lot going on with this. It's neat that you can push on the damper and actuate the mechanism. I will admit this is way, way more than I was expecting in getting into this, and I'm absolutely fascinated. This is so beautiful. Hell of a bit of work for 1994, huh? Oh, cool. Well, thank you guys for hanging out with me on this one. That was a ride. That was more than I bargained for. I expected this to be the quick, easy autopsy of the day. I'm actually shooting a couple today, and I expected this one to be super easy. There is a lot to that, and I have all kinds of really nifty little brass gears and parts and stuff left over as a result. So you're going to see these in some manner of pretty project in the future, I'm sure. Thank you guys for hanging out with me on this autopsy. It was a lot of fun. And if you like this kind of stuff, subscribe. get involved. If you check out the links below in the description, because I know everybody's like, yeah, man, just click that like button and subscribe. No, if you like this, subscribe it. But the big thing that I want to invite you to is there's a whole community around this. It isn't just the videos of me talking at you. I want you talking back. I want a dialogue. I want to communicate. I want to build a community. And if you check out the links below in the description, I actually have a Discord, and you're invited. And while I'm shooting this here on camera and you're watching this weeks, months, years later on YouTube, there's actually a group of people hanging out live in real time, and I can talk to them and they can talk to me, and you can be a part of that. Check out the Discord link in the description, and if you subscribe, there's a lot of these that are done live. So I shoot the production video with the cameras and that, but we're also on a live camera up there, and you can be hanging out. It's kind of fun. If you're into nerdy stuff, it's a fun time. So thank you for being a part of this. Thanks for hanging out and watching my silly little video. And as always, we'll see you next time. Okay, 3 camera sync in 3, 2, 1. It's almost like we're fucking professionals over here. Oh my God. This is the most thrilling part of the fucking video. All right, well, we can't get in the front door. Let's see if we can go in the back. Oh, it's tight in there. Let's find the fucking microscopic screwdrivers. I don't know if fucking tool will work for this, but I have a tool for this. Try to get it to fucking focus. Focus, you fuck!